Okay, everybody, so I just want you to look at the calendar to begin with. So right now we're going to cover chapters 28 and hopefully get through 29. Now 29 is really long, and so I strongly recommend that you watch this chapter 29 pre-lecture to get a fuller understanding, particularly an intuitive understanding of how analysis of variance, that's what 29 is about, for regression fits with analysis of variance that we did already for comparing means. So let's go to the document camera and begin. Okay, so the last thing we did was confidence intervals for the slope. If you remember, we were looking at this example where we took a random sample of 25 students from all U of I students because we were wondering whether there really is this negative correlation between drinking and GPA. So we thought, does drinking more hurt your GPA more? Is there a negative correlation? Now remember, so what we said is what we're going to do is we want to estimate the correlation in the whole population. So we did that through our sample of 25. We don't have the money, the resources, and everything, time to interview all and survey all 28,000 undergrads. So we took this random sample of 25, and from that we got these statistics here. And we saw, yeah, there was a negative correlation, but it was pretty small, negative 0.2. The question is, would it hold up in the whole population? So what we did was we put error bars around that. Okay, so we said, here's how from these statistics, we got a slope here, and we put error bars around this slope. Is this a strong enough indication that it would hold up in our population? So we did R that we got in our sample times SDY over SDX, and that's what we got. And remember, the interpretation of it is that for each drink these are drinks per week, so for each extra drink that a student drinks per week, on the average it would lower their overall GPA by that amount. Okay? So, so what did we do? We wanted to calculate, we want to put error bars around that, so we want to say, okay, every time we take a sample, we're going to get a different 25 points and a different correlation. All the points will be different, so we're going to get a slightly different correlation, etc. And how much is that going to vary? How much is our slope going to vary? So we looked at this as saying, okay, this is the error bars around our regression line, and this is the size of our sample, and then we're using that SDX to put it into the same units. And we got this. It's going to vary plus or minus this. And from that, we built confidence intervals using the normal curve or the T curve. We're on the borderline here with 25 students, so I think we did it both ways. And we put, error bars at 95%. We got this critical value of T here, 2.07, right? And then we used our critical value of Z, which is really 1.96, but we rounded to 2. And we saw that, yeah, we get a little bit narrower confidence interval with the Z. But the basic idea is what? We got this point estimate that was negative. But when we add and subtract our margin of error for 95%, it actually includes 0, right? It even goes up to a slightly positive slope for both of them. So what does that mean? That means that we really can't tell if there's a negative correlation. We're not 95% sure that if we polled everyone that there'd be a correlation of a negative correlation or a negative slope. And so we said, since our confidence intervals include 0, we can't be 95% confident that there's a negative correlation in the population. In other words, the small negative slope in our sample could easily be due to sampling error. And so then I said this. I said a 95% confidence interval, including 0, is the same as not rejecting the null hypothesis. So that's what we're the null hypothesis that the true slope is 0 against the two-sided alternative at 5%. And so that's what we're headed into. The next chapter is doing the hypothesis test. But let's just visualize this for a minute. So you remember a 95% confidence interval. Let's just draw it. Let's just use the normal curve. Okay, so once we convert it to our test statistic to a z-score, it's right 0. And now we have 95% in the middle. So what we're saying is if it includes 0 like it is, then what that means, so that means that we're somewhere in here in this range, which means that even if we're out here and we think it's negative, we got evidence it was negative, when we build our confidence intervals, it includes 0. So we can't reject the null. Now, if it was out here, in our p-value, what are these p-values? If it was out here for a one-sided test, our p-value would be 2.5%, and then we could reject. If we went over 2 standard errors, we wouldn't include. Outside this range, our confidence interval would not capture 0. So if if it's in this area or that area, then we would reject the null. If our sample slope, just our sample slope, landed in this area or this area, then we can reject the null and say, hey, right? But if it lands inside here, we can't. That's the point. So this is for a two-sided, it's 5%. So, okay. So again, this is a two-sided. What if it was a one-sided? What would a one-sided look like? In this case, our one-sided would be beta, the true population slope, is what? Less than 0, negative. Because we have a suspicion ahead of time. We don't think drinking is going to improve your GPA, unfortunately, right? Otherwise, we'd all go out and get drunk, come to class drunk, and have a good old time. And we'd all get great, it would be fun. It'd be like the one day I taught on unofficial where everybody's drunk and so enthusiastic, right? But they didn't learn anything. So we think it lowers it. So that's why we have the one-sided. So then if we have the one-sided, we know it's the equivalent of only half that. So for one-sided, it would be the same as at alpha equals 0.25, half the p-value. Because we're only looking at one tail. Okay? Do you understand? And we've already been doing this. Let's just check out our t-table. I mean, we've been doing it because our t-table gives us one-sided p-values. And we said, hey, look, a one-sided p-value of 2.5, a one-tail test, 2.5%, that's like a 95% confidence interval, right? We've already been doing this. It's just all along. It's nothing to do with slopes. This is what we've been doing all along. So I'm just making it more explicit now because you're getting used to all this stuff. So now let's just jump ahead and do the test. So where would it go? Okay, so what would be the difference if we did if we wanted to do a hypothesis test? Well, let's read first. So now we're on page 135, significance test for the slope. Okay. So sometimes, instead of finding confidence intervals for the true population slope, given the sample slope, just getting an estimate, we're not really concerned whether it's 0, just getting an estimate and building, we just want to get a p-value. This happens a lot for the null hypothesis that the true population slope is 0. So we ask, if the true population slope was 0, how probable would it be for a randomly drawn sample slope to be so different from that slope of 0 as what we got in our sample? And that is how we do a significance test. So looking back here, and here's the test statistic, and I'll explain. This looks complicated, but it's really not. So let's just jump back here and pretend on this same thing we were doing a significance test. So we said, what would the null be? Let's just think about it. The null would be that in the population, there is no slope. That would be the only difference. We didn't make that, so our H null would be that there's no slope, and then we do an alternative hypothesis. right? But we'd set it up the same way. We randomly draw 25 tickets without replacement, etc. All right? And then we'd have these sample statistics, and from them we could get a sample regression equation. Here we got the slope. We could get the whole equation if we wanted. And here we have the standard error. And what would we do? Well, let's think about it. Let's jump ahead and just do it intuitively, and then we'll see how it matches up with what we're supposed to do. All right, it matches up with that. Okay. So let's just jump ahead to that same example on page 136. See, everything's the same. So we have the n equals 25. We have we got this in our sample. And so now, what's the difference? So now from our sample, after we check the assumptions, we have to do all that, but we already did it for the confidence intervals. Okay, so now we're going to go straight to, we computed this. If you forget how we did that, like the slope here, what did we do? Boy, I put it in the opposite order here. I'm sorry. This is the same thing. I put it in this order, like the old-fashioned way you learned it in high school, like mx plus b. It's because I copied it from Stat 100. So it's like this instead of the way we usually write it in statistics, b naught plus b. That's okay. So this is b1, and that is our intercept there. Okay, so now we want to get the slope, b1 over here, or I'm just calling it 1 because multiple regression, where we're going to have b2, b3, etc. But you can just call it b because we only have one of them if you want. And this is our slope. And remember, this is something you really need to know. So I'm writing it down again. R times the standard deviation of y times the standard deviation of x. So that's going to be our sample slope. And it's exactly what we got before, but I'll do it again. R is negative 0.2. And then which one's y and which one's x? We're predicting GPA from drinks. We're saying the more you drink, the lower your GPA. So this is y, and that's x. So then we have this ratio of the two standard deviations. And we got, sorry the numbers look so similar, that's just a coincidence of that. And that's our slope. For each extra drink, that's how much your GPA is lowered. Okay, so we could put that in here. And just to remind you, and points per drink, then the drinks cancel out, right? And you're going to get GPA in terms of points. So what's our y-intercept? Our y-intercept, you remember how you do that? You plug in the point of averages, so we'll do that. And we solve. So average for this is 3 equals negative 0.2 times the average for the drinks is 10 plus what? Negative 0. Oh, look what I did. It's so easy to do because these are so similar, right? Negative 0.02 times 10 plus b naught, and we see that b naught is 3.2. Okay? So that's what we get. Now, all right. Now our null is, so at this point we built confidence intervals by doing it, but let's just do, now we're going to do the hypothesis test. So we come up with a null, and here's our null right here. And what does that mean? It means in the population, if we were going to draw a scatter plot, like we did before, our hypothesis is we have a completely flat line here. R equals 0, our slope equals 0. So let's just draw it, just so you can picture it. The null is always about the whole population. So we have inside here, we're going to have a scatter plot about the whole population that will have, this is our null model, like a box model. So imagine we have drinks, how many drinks, and GPA, and it's about the population. So we're going to have 28,000 points in here. Whoa, that's a lot. But just imagine 28,000 points. Okay? So our scatter plot has, the scatter plot has 28,000. Why did I say 28,000? Because there's about 28,000 undergrads. So it's one for each UIUC student. undergrads. Okay, so that's what we have in here, 28,000. And then our null says that inside here, we have a completely flat slope, right? A completely flat slope. So this says, that's our null, that H naught is equal to 0. It's the same as R equals 0, okay? Because when the slope is 0 if and only if R is equal to 0, same as R equals 0. Completely flat, no correlation. So what does that mean? It means that no matter how many, it's not going to help you or hurt you. No matter how many drinks you have, your GPA is not really going to be affected. That's what it says. And so what would this line be centered at? Can you intuitively, you probably know that it's going to be the average right here. It's going to be this right here. This y, the intercept, this is the same as saying what? H naught is the same as saying what? That we could predict your GPA based on the average. That y is equal to y bar, the average GPA. Because no matter what, we're not going to predict, knowing how much you drink, X isn't involved. Knowing how much you drink has nothing to do with the GPA, so we might as well predict the average for everyone. Another way you can see this is when we plugged in the point of average. If this is 0, right? If this is 0, when you plug in the point of averages, you're just going to get the average of y. That's going to be 0. Will be your y-intercept. So that's what the idea is. That's the same. Those two things are the same. All right. That our regression line here, of course there's scatter around it, plus or minus something, but that's our best estimate. Okay, so now what do? We take out 25 points from here, da-da-da-da-da, we take out boom, boom, boom. Sorry, looks like a mess. But then we get these 25 points. And so in those 25 points, there's a very slight negative slope, okay? We get R is equal to negative 0.2, or B1 is equal to negative 0.02. That's what we got. We got this, we get these statistics. The same thing, drinks and GPA. And so our question now is, what test statistic would we use to test this? Okay, well our usual test, let's just do Z first. Our usual test statistic would be what? Our observed value minus our expected over some standard error, right? So let's see what that would look like. We'd get our observed slope from our sample minus the expected under the null, which is 0, right? Under the null, that's 0. And this is B1, right? Our observed is our sample slope, over some standard error for the sample slope. And it would be not plus here. We're just going to say standard error for the slope, for B1. Standard error for the slope. So that would be it. Okay? So it's... So, and what would be our t? If we wanted to do a t, it would be the same thing. T would be our observed slope. Everything would be the same, minus the expected slope, which is 0, over what? Standard error plus for our slope. Okay, so how would we do this? So let's just work out what we would get. We could take our observed slope right here, minus the expected slope, and then divide by our standard error for the slope. But let me just do it in general, okay? So you can see, because there's an easier way of doing this. So let's just do it in general. So we're going to say Z is equal to our observed. Let's just go back to R. This is how we do our R times SDY over SDX over... Now, do you remember what our standard error for the slope was? You probably don't. It was the standard deviation of the errors right? Which was the square root of 1 minus r squared times the standard deviation of y. It had that square root law over the square root of n. So SDR is over square root of n, but then we had to have it match up to the slope, so we did this, SDX. I'm going to, this is a lot to remember. I'll give you this on the exam, the standard error of the slope. So this one will be given to you. Okay, so that's what I just did. And this is given on next exam. There's a lot to remember. So this will be given on exam 2. I'll remind you. I'll send you what will be given, what won't. Okay, so anyway, so that's given. And then we change it slightly for the t. Okay? But let's simplify this. You see, let's simplify this. Do you see how now these standard, you have an SDYX here and an SDYX there. That makes it a lot easier, right? So now, and then let's just simplify this and multiply the top and bottom of the fraction by the reciprocal. So then this is equal to what? R over the square root of 1 minus r squared times the square root of n. So that would be our test statistic, right? That's what we would intuitively think. And if we did it with t, it would be exactly the same thing. What would be different? Nothing would be different except for this n here, right? You'd get the same r sdy over sdx. I'm just writing it over and over again so it sticks in your brain. And the same square root of 1 minus r squared times the standard deviation of the y. But here is where it's going to get different. It's going to be, we have to tweak it because we have a small sample size and the central limit theorem didn't kick in. So we change this to the we change it right here to n minus 2, the degrees of freedom, over sdx. That's what we did. But everything else is the same. And now we get this, r over the square root of 1 minus r squared. And now it's like we have a little bit smaller sample size. We don't have quite as much evidence to reject the null. See, this is why you get more evidence. It's easier to reject the null using this one than this one. Because it's like you have a little bit smaller sample size. All right, so that's it. And then we'd go ahead and we'd compute our statistics. Okay? And what would be, by the way, well, let's just go ahead and do this now. So for z, what would we get? It would be pretty easy. What we're given are right here. So that's negative 0.2. And then we're given, and then it's over the square root of 1 minus that squared, negative 0.2 squared. And then it's times the square root of 25, which is 5, right? So I did that, and I got 1.02. And here we do the same exact thing, except instead of multiplying by, this is going to be exactly the same, but instead we're going to multiply by square root of 23. So we'll get a little bit smaller. Okay, so we'll get negative 0.2 over the square root of 1 minus that squared, negative 0.2 squared, times the square root of 23. And here, this is negative, of course, sorry, because it's a negative here. And this is negative 0.98. So these are our statistics. Okay? So we're a little bit further out on the tail here with the z. We need less evidence to reject the null. All right, now let's see how this matches up with what I wrote here that looked kind of complicated. It's exactly the same thing, right? Right? I said the slope minus, I didn't say minus 0 because we always, the expected slope is 0. And so it's the same as what we have here, okay? And what I say, so let's read it. And just to remind you, I'll just write it here. T is equal to the observed slope minus the expected slope over the standard error plus for the slope. And under the null, the expected slope is equal to 0 under the null. That's the idea. And same here. Okay, so that's why we just have a b, not a b minus something, not a b minus beta. All right, so we've got that, and then we're going to attain this p-value. And look, our test statistics end up involving only r, not this. And does this procedure fit with what we said our hypothesis testing usually means? Yes, we just did it intuitively. And does it give the right answers? Yes, it will. So that's pretty much it. Okay. So remember, just to write it down again, 95, okay. We attain a p-value. For a one-sided test, we'd have one tail. And for a two-sided, this is one-sided, would be one tail. In this case, if it's less than, it could be either one. This is the one-sided. And the two-sided p-value is exactly the same thing, but with two tails. All right? So if it's 95% confidence interval, this would be 2.5 and 2.5. And that would be a 95% confidence interval. Confidence interval. Not including 0, like if we get out here, not including 0. This is 0 in the middle. If we land out here, not including 0. 95% confidence interval, not including 0, is the same thing as what? That would be our sample stat, our test statistic landed outside here, and that would be the same as rejecting the null, rejecting H naught at what? 5% at alpha equals 0.05, right? For a two-sided test. Which would be what? Beta not equal to 0. Because our null is beta equals 0. For a one-sided test, it would be like rejecting it at what? The 2.5, it would be like it would be like 97.5. All right. So you understand that. All right. Now, any questions so far? Do you know how this would be? If you had a one-sided test at 5%, that would be 5% there, which would mean 5% there, which would be 90% in the middle. So it would be like a 90% confidence interval, not including 0, is the same as rejecting H naught at alpha equals 0.05 for a one-sided test. But since we always do these, like, usually 95% confidence interval, it's the same as that, or, I should write, okay, for the two-sided, or rejecting H naught at what? Alpha equals 0.025, just one of the tails. You'd have, right? Rejecting alpha for one-sided test. Okay? Because you already know it's all the 5%, all of your uncertainty is in one tail. So it would be as if you had 97.5. For confidence interval is always symmetrical. That's all. That's the easiest thing to remember. Confidence interval is equivalent to the same two. It's a symmetrical. You're adding and subtracting the same margin of error. Yes? Why is what? What is a one-sided test? Rejecting the null at alpha equals 0. And only half. Does that make sense? Because if it was 5%, then we'd really have a 90% confidence interval. just our two-sided alternative lines up with the same, lines up very nicely with a confidence interval, because the two-sided is symmetrical, and so are confidence intervals. And by the way, most software programs automatically do the two-sided. So that's usually how you think of it. All right, so now we didn't do the test yet, did we? Now we saw it included 0, so we're not going to be able to reject the null when we do this test. All right, so we're right here. We got our test statistics. We're right here, and now what are we going to do? Let's turn the page, and we can use these. That explains it all. And now we can actually do the test, right? So let's do a z-test. And for our z-statistic, we already got negative 1.02. And so we just want to get, let's approximate, okay. So here's 0. And negative 1. It's just going to be almost at negative 1. So it'll be very close. This is that. That's our statistic. And now we want to get a p-value. So we just want to get this area. If it was exactly 1, it would be about 16%, but it's a little bit less than that, right? It's a little bit further out than 1. All right, why don't we just do it on the p-value calculator? So let's just do that. We'll go over to the p-value calculator so we can get a more exact. All right, so what did we say? Our z-score is negative 1.02. And what do we want? We want the left tail. Be careful here. And we want our p-value for the left tail. So there it is. It's a tiny shade over, and it's 15.39. All right, so that is our p-value. Let's write that in. And let's go to the document camera. So this is 15.39%. So that we can't reject the null. And our confidence interval, of course, includes 0. We saw that, so that agrees. So now let's just try the t and see the difference. So what was our t? Our t, these aren't critical values. The actual t stat was a little bit smaller because we have a bigger error we divided by. And so that's negative 0.98. And now, which t-curve should we look on? We need the degrees of freedom. And remember, what are the degrees of freedom? Do you remember it's n minus the number of parameters, n minus p? How many parameters do we have in this model? What is our model here? Our model is what? Is that y equals beta naught plus beta 1, x plus some error. And these are the two parameters that we're estimating. So p is equal to 2. And n, or as our sample size, is 25. So we have 20. Wait a minute, did I do that? Right? Yes, 25 minus 20 minus 2 is 23 degrees of freedom. That's our degrees of freedom. Because it's n minus 2. Just to refresh your memory, didn't we talk about this? Yes. The degrees of freedom is n minus the number of parameters in your model. Right? So if we have variance around the mean, n minus 1, because there's only one parameter in our model, mu. We're just estimating the mean. But when we have two parameters in the model, like 2 points determine a line, we have 2. And when we do a plane, we're going to do n minus 3 each time we add a variable. Okay, so here we're at those degrees of freedom. So what does that mean? That means, why is that important? Because there's a different t-curve. That's why I love the normal so much. There's a different t-curve for every degree of freedom. So it's a little bit fatter in the tails, but we have a big enough, I drew that poorly, but we have a big enough degrees of freedom. Remember, our cutoff is about 25, so it's going to be very close. Let's check it out. So let's go to the, let's just, so much easier to look at it here. All right, so I wish I could give you this on the test, but we can't do this. So, all right, so we're going to do a t distribution now. So we have 23 degrees of freedom here. And now we want to get what? Our t statistic was what? Negative 0.98, right? And so we want the left tail. Be careful here. We're just looking at that. So we'll compute the oh, there it is, 16.86. Okay, questions? So let's put that in. So we'll go back to the document camera. And so we have this right here. That's what we're looking at. And we get this. And it's 16.36%. So we cannot reject the null. At 5%, if we look here, small values appear evidence against the null. They indicate our observed difference is too large to be explained by the luck of draw, so we reject the null when p is small. How small? And if we're going to just use our usual ones here, we can't reject the null because our p-value, this is our p for both tests, because our p-value is greater than 5%. So this means we really cannot rule out. This might be good news for drinkers. We cannot rule out that it might make no difference in your GPA. We cannot rule out that beta 1 is equal to 0. Now, don't go out and drink and stuff, because there's other issues here that I didn't talk about, but don't. Plus, it's terrible for your health. So I'm not advocating that. I'm just saying in this population, if you look, just one, we're looking at a very restricted range of students, because this is about the data we get. You're already good students. So pretty much you can kind of, the correlation isn't going to show up in this restricted range of really good students. You already did so well in school, so probably it's not going to, you don't really see the effect in restricted range. If you look at all high school students, you'd see a big negative effect. It's just that you're in this restricted range of students who already get such high GPAs to get in here. It doesn't, if you know how to handle drinking or something, it's not going to show up. We'd have to have a much bigger sample size. It probably is negative, but it would be a smaller effect in a bigger sample size. The idea, just because it's an interesting idea, it's just this. Like if you have, like, let's say we have this negative correlation across a whole population, right? And we do have some negative correlation, and this is drinks, and this is GPA. But we're just looking, yeah, if you look at this whole thing, you see it. But we are looking at this group who has incredibly high GPAs to get in here. So you're way up here. And if you just look at that cloud here, you might not see very much. That's what's happening. Does that make sense? It's a restricted range, very small range. So we don't see enough happening. Your GPAs are really high. Okay, so now that's that. And ta-da, we're done with that. So here's our summary. Read it. Okay. Extremely important. I'm just going to say read because you have to read all of these. All right, and now we're going to look at an analysis of variance. Oh, I just have to take a tiny little break here. Just to those watching at home, I just want a minute just before we dive into this. So any questions right now? Anything at all? Nothing. You guys understand? Nod. Tell me. I love that you're here, so participate and ask questions if you want. Nothing? Yes, go ahead.
1 hour confident interval now including the error.
What?
1 hour confident interval.
Our confidence interval did include 0 here. Did I say it didn't? Whoa, good catch. Let me see if I did do that. Let's go back. I didn't say anything here. Cannot reject the null. That, when we cannot reject the null, what does it mean? It means that it could be 0. And if we actually built a confidence interval, a 95% confidence interval, remember it would go out to here, like about 2. Look where, and it would land in. So our confidence interval would include 0 here. We cannot reject the null. You reject the rejecting the null is when did I say it wrong somewhere? Rejecting the null is when our confidence interval does not include 0, just in general. If our sample landed outside here, if our sample statistic was outside here, we reject the null. And our confidence interval doesn't include 0. Our confidence interval does not include 0. It's outside that. Do you see? Does that make sense? I mean, basically, if you run, okay, so we land out here, and then we add 2 standard, let's say we added 2 standard errors, see, it wouldn't reach it. It wouldn't include 0. Does that make more sense? Good question. Okay, I just switched the direction here, right? It's so much easier to think of the picture than the words, right? See look, if we were doing a confidence interval, look where it landed. If we were doing a confidence interval, we'd have to get outside that range, outside the 5%, right? If we were doing a one-sided, it would be outside the 2.5% range for a 95% confidence interval. We'd have to have 95% in the middle for a z-score. We'd be at 2. We'd have to land over there, which would be, should I draw it? Do you want me to draw it, or would that be more confusing? Do you get it or not? We'd have to land, imagine, I'll put little things in. So our 95% confidence interval would have 95% in the middle. This only has like 68 in the middle, 95% in the middle. And we'd have to, that would be 2.5 and 2.5, and we'd have to, for a one-sided test, we'd have to get a p-value less than 2.5%. Does that help? Good. All right, any other questions before we go on?
Wait, can you repeat that you said?
I'm sure I can repeat it. I can just repeat it with a picture like this. All right, think of it this way. 95% confidence interval, just draw it, right? 95% has how many on the tails? 5% on both tails, right? 5% together. So that means 2.5% and 2.5%, right? So now if we do a test statistic and it lands either here or here, we're going to reject the null. And that's the same as landing outside the 95% confidence interval. Does that make sense now? Any other questions? By the way, you know what? You really should, I'm taking a deep breath before we go into the next section because there's a lot to explain in the next section. And what I do in the video is take it, I'm at a blackboard in the pre-lecture, and I can explain it much better than I can and relate it to things much better than I'm going to be able to here because it's just so dense, it's like more like a textbook. I'll try, but I strongly recommend that you watch Prelecture, chapter 29, because then I'll really explain it with a big blackboard and more. You'll see, the people at home, you'll see me. And I'll hopefully tie things together more. That's what I try to do. And I made it extend the due date so it's not due till Saturday night, so you get more of a chance to do that. But let's go into this. Okay, so we are going to start this. Okay, so we've already used ANOVA in the particular situation of comparing means. Remember? Now, we're going to see how ANOVA provides a basic framework to assess the fit of all predictive models, linear models, as long as certain assumptions are met. Okay, it's the assumptions we've been checking. It checks whether adding parameters to a model, adding predictors to a model, adding slopes to a model, or adding more groups, or adding more variables, more predictor variables. Making it more complicated actually improves the accuracy of the predictions significantly, more than would be expected by random chance under the simpler null model. Now, the simpler null model that we're doing is the simplest null model of just none of the slopes have any, or all the slopes are 0. Basically, we'll do just as well predicting some quantitative y variable by the average of the y's. We're just not going to go into different levels of simpler models. We're just going to do the simplest, strictly just the null model. That's just everything 0. Okay, and it yields a test statistic called the F ratio. That's what we saw to compute these p-values. So how does it do this? We've already seen this. We've already seen this. What does it do? This is the main idea. It breaks down this variation of the y into 2 parts, the model and the errors. It basically, you could think of it as the variance of y. What it does is it's this. The sum of squares. This is, basically you have some model, either this for ANOVA, that's what we've seen, the sum of squares total is equal to the sum of squares between plus the sum of squares within. If we wanted to talk about the variance, we would just divide this by n all the way through. But people, it's the same thing. Now it's like the variance multiplied by n. If you wanted to do it with that's why I call it variation. If we were doing it with variance for both of these, what would it be? It would just be, if you wanted to do it with variance instead of variation or variability, just so you don't get confused, the variance would be what? The variance of the y's is broken up into these 2 pieces. So you have sum of squares total divided by n is equal to sum of squares model divided by n plus sum of squares error divided by n. And then you just multiply everything through by n to get rid of these. Most people do, and then you're left with this variation instead of the variance. Okay? This will just confuse you, though. In the video, I have more space, but that's the idea. So that's why I'm calling it variation or variability instead of variance, because I haven't divided through by n. It's just simpler to do the sum of squares. All right. So now, it breaks up the variance of the y's into these 2 parts. And here we had, so why am I saying it's a model here, sum of squares between? Why is that a model? It's because if you think of it as a predictive model, this is a quantitative variable. Let's say it was exam scores. And this is some categorical variable predicted by the group means. So we say the variance of your exam scores are going to be predicted by the group mean. Like, for example, there's 7 different sections of you're divided into 7 different sections. You here are in L1, people watching at home are online, then there's all the TA sections, so there's 7 of them. So maybe we think which section you're in will affect your exam score. So we could say, we could predict, this looks at the differences between the group means, the 7 group means, and makes a prediction solely based on the average of the group of the, if you're in this section, the best prediction would be the average of this section. If you're a TA section, that particular TA's average, etc. Plus, then what's this? This is scatter around the group means. That's what we did. So this is our model. Our model is a categorical variable predicting a quantitative one. Okay, that's the way you should look at it. Now, what are we going to do? Now we're going to look at how a quantitative variable predicts a quantitative one. So now we're saying our final exam, let's say it was final exams. Now I'm saying final exams is being predicted by midterms. That was our example. Okay? So we're saying now, so you have this variation in the same thing as this. You have the same spread. But now we're saying it's being predicted by a quantitative variable, what you got in your exams, how that's going to predict your final. So that's our model, the regression line. That is our model, the slope we get in regression. Okay? The null is that that's bogus, but that's the model. So the variation predicted by a regression line plus the variation of the errors. It's the same thing. Does that make sense? Does that make sense? Okay, good. And we use the same f-stat for both. Okay? So it's just, you're going to see that what this is a special case of that. This comparing means is a special case when you have a categorical variable of regression. Okay, so now for simple linear regression, you're probably wondering why we are doing this, because we just did a hypothesis test using Z and T. So why am I doing this? Well, analysis of variance is just another way to get the same p-values for the slope that we got from the Z and T test. You're going to get the exact same p-values. I just want to, but it's a good idea because I can show you in 2D what it looks like. Whereas when we move into, in multiple regression, it's not going to be the same thing. In multiple regression, we have to use an F statistic. We're going to have multiple slopes, and we can't use Z or T, right? We can't do that anymore. We're going to have to look at the whole, all the slopes. Some might be positive, some might be negative. We have to look at the collective effect of all, just like we do with group means. So I'm just going to explain it in the simple case where we already can use a Z and T, so you can see it, okay? So here we have all this and blah, blah, blah. Okay. So these are all the same things. And here's our null and alternative. And we're asking, does adding a slope make a significantly better prediction of y than just using the average? Because the null is, that's what we're asking. The null is this. This is the same thing as, does it reduce our prediction errors significantly? That's all we're doing. All right. So let's go and look at it visually. All right. So, here we have the variability. It's what we did before. So let's look at it in the context. Okay, so what is this? This is like the first step on the way to computing a standard deviation. You take your deviations, take each y, and you subtract it from you subtract off the mean. And if we just added all those up, they'd sum to 0. So we have to square them and then add them up. And then if we divided by n, we'd get the variation. Okay, so what is SST? So SST is equal to our standard deviation of the y squared. That would be the variance, then multiplied by n. That's the relationship there. That's the same thing. Okay, so now, what are we doing here? And then we're going to break it up into two pieces. We're going to break it up to our model, which is our regression equation, our sample regression equation. Does it do better than just predicting the average? Okay? So we get this model here. That's our regression. So this is our model, right? And here we're doing the same thing. Let's just do the same problem. So our model was what? That the predicted y is equal to 17.99, let's just say 18, it's easier. That was the beta naught we got before, plus 0.67 times the exams. This isn't our drinking example, this is exams predicting final, the one we did before. And that's the same thing. Okay, so now, where did we do this? Didn't we do this one? Oh, sorry, where did we, here it is, it's this one, that one. Okay. And here we did, oh, look. Yeah. Right. Okay. So anyway, so let's do it here. All right, so now what are we going to do? You know, I think it's easier if I color code these things. So we're going to break it into the model and the error. So let's make the error yellow here. And let's just make this model blue, and we can see the picture of it. Like we did, we'll do the same thing that we did before for analysis of variance, where we had yellow and blue, and where was that? Did we do it? Here, we'll do the same thing. Okay? And we're just going to compute it from scratch, same way. But now our model's a regression model. All right, so what can we do here? So first of all, so this is our model right here. And so our error is how far our actual points are observed minus our predicted. So it's going to be like that's error from our model. This is our model. So that's error, how far our actual point landed from its predicted, right? And here's our actual b, and there's where we predicted it to be. oh my God, we did terrible on C. We predicted C here, and our error is huge. And here, that's our error. Here we had no error. It landed exactly where we predicted. Okay, so this is our little bit of error here. There's an enormous error. We predicted below average, and we got above average. That student did much better than expected. This student did a lot better, too. And this one got exactly no error. I can't even see an error. Okay, so what is our, so the question is, that's our error. And where's our, so we're breaking the total, like if we take a particular point. Okay, let's look at our model first, though. So what's our model saying? Our model is saying how much better does our regression line do than the overall average. So here's our overall average, y bar. And we're saying, look at our predicted. How much better does it than if we just did the average, 74? Well, we predicted this is how much better we did. And then together, this plus this is the deviation, how much that point deviates from that. So this plus this equals the total deviations, all right? So here, our model did pretty good, and we had a little bit of error. Here, we would have done better without the model. We would have predicted, we would have gotten closer without the model. Okay, so our model didn't do very well compared to the error, and here, our model didn't do great. And here, our model did perfectly. There's no error. Okay, so that's the idea. So for any particular point, before we square them, for any particular point, like let's look at point D, that's which one is that? This one? What is it saying? The D, the overall, 95 minus 74, that's 21 points, and we broke it up into the yellow part and the blue part. And the blue part is 80 minus 74, which is 6, and this is 15. So you can see that before we square it for each one of these, it works out. And when we square it, it does because of, well, you can look at why. It's basically because of independence of the errors. The cross terms cancel out, and this does work out too. And you can look at the proof for that in the back of the book. All right, so that's the idea. So now you got the visual, so let's do a computation, not with all these points, but let's just take a simple one. You'll have to do this on your homework. So let's do this. So let's illustrate how analysis of variance works with a very simple example. Suppose we draw a sample of n equals 3 points from a large population. And here's our 3 points. 1, 1, 2, 6, and 3, 5. All right? We don't know what the population looks like. We got these 3 points. And then we fit the best fitting line, the one that minimizes the sum of the squared errors, through that, and that's what it is. So this right here is our regression line. So those are our predicted values, right? So let's see what they would be. So for 1, you'd plug in 1 here, and our we'll get 1, 2. That's where we get this, right? For the next one, we'd plug in 2, and here we get 2, 4, and the last one we get 3, 6. That's our line. So that is this one, 2, 4, and 3, 6. All right. So those are our errors, these, and we're going to square them. All right, we can put those in. This is an error, and this is an error, and that's an error. That's the size of our errors. Okay, so now what is the overall? What's the average of the y's? We didn't do that. So we have to do y bar. So y bars, you just take all your y's here. 1 plus 6 plus 5, which is 12 divided by 3, and we get 4. So let's draw that in. That is y bar equals 4. Okay? And that is going to be our model, right? Our predicted minus, it's this. So this is like, we predicted this. How much better did we do than the null-dull model? Did our model, this is our model, improve over meaningless, having no model at all, the null? Okay? Did it do anything better? Okay? Here, it would have done, doing nothing, we would have gotten the right point. Instead, we're the observed. Okay, so that's all error. And here, our model is what? So did it do better? So here, our model is this, right? No, it's this, right? How did our model do compared to that? It's that. Okay, so now, let's do it. Oh. So what do we want to do here? So it's y, all our y's minus, so for each of these it's minus 4. Okay, minus 4 and minus 4, because we're subtracting off the average, and these are just our values, right? They're 1, 6, and 5. Our y values, 1, 6, and 5. So that's 1, 6, and 5. So what do we get here? This is just how far this point is from the average. That's negative 3. It's below, right? And this one is 6 minus 4. It's 2 above. Okay? And this one is our point from the average is just 1. And you know what? Okay, so that's, before we square them, they should sum to 0. Okay? Let's do it for all of them before we square them. Let's just look at these deviations, what we have up here. All right, so the next one is what? These are our predicteds. Still minus 4, and minus 4. But now we're going to use these predicted. These are the hats. So that's 2, 4, and 6. So here we get negative 2. Here we get 0, and here we get 2. Notice they sum to 0 too. This is why we're going to have to square them. They're all going to sum to 0, all the columns. And so here, wait, what are we going to do here? This is our actuals, 165, minus the predicteds, which is 2, 4, 6. So we get negative 1, 2, and negative 1. And they have to sum. So let's write that down. Let's write check, because that's really good before we do anything else. Check that the columns sum to 0 before squaring. That's why we have to square. Otherwise, we'd get 0 for all of them. It would always be true, no matter what it is. All right, so we square these. So we take this, and we square, square, and square. And what do we get? We get a 9, a 4, and a 1. So we get 14. That's our total sum of squares. And here when we square them, we get 4 squared is 0, squared is 4. So that's 8. Now they're going to have to add up, so you know this is going to be 6, but let's check it. So you square this, square them, and square, square, and we get 1, 4, and 1. So it all adds up. So it checks. Hooray. Now you can see why I didn't want to do this with more points. It's just so tedious. All right? Questions on how to do this? So what we're going to be doing is comparing the ratio, basically, of the blue lines over the yellow lines. You can see we're not going to get much significance. Look how big the blue is compared to the, doesn't do much better than the errors. Okay. Remember, you need an F ratio of bigger, much bigger than 1. All right, so now let's see. So the ANOVA table is a handy way to illustrate how the sum of squares are partitioned. All right, so let's just fill in this. We did this from scratch, and let's fill in the ANOVA table now. So what do we have? We have 14, right? And our sum of squares model is 8. And this, our error is 6, and they add up. Our degrees of freedom, we have how many parameters we have? We have 2 parameters here, 1, 2, p equals 2. So p minus 1, This is going to be 1. 2 minus 1 is 1. N minus P, we only have 3 points. N is equal to 3. That's crazy. That's why N equals 3. You have 3 points, so that's 3 minus 2, so that's also 1. So here when we do this, we get 8 divided by 1, that's 8. 6 divided by 1 is still 6. So our mean, this is 8 divided by 6 is our F ratio. And that is equal to 1.33. That is not going to be significant. Nowhere near significant. What do we have to do to get significance would be much, much bigger. All right, so we only have 3 points. We're going to have to get something much bigger than that to get significance. Okay, so now let's zip ahead. And I didn't think I was going to get this far, but we did, so this is great. All right, so I'll just go ahead and do it. Now, remember how way back when I said this R squared is going to feature in all regression analysis? Way back when I said it's going to be really important in all regression analysis. And I say the square of this correlation coefficient is another way to assess the fit of the model using the ANOVA table, because what is going on here? Basically, remember we say that R squared is the proportion of the variance due to the model, and 1 minus R squared is the proportion due to the error. Basically, we have this sum of squares total here, right? And this plus this adds up to that, right? So, so this SSM is R squared times SST, right there. And this, as the error here, is 1 minus R squared times SST, and together they add up to SST. You can see that. I'm sure I explained it back here, and I explained it in the video. I want to see if I already have it written down in here so I can show you. When we did the, let's just see, when we did the, yeah, here it is. So remember I said R squared, this is on page 126, is called the coefficient of determination. It's the fraction of the variance of the y that's predicted by the model. Right? R squared is a fraction of the, okay? So I said the standard deviation of the errors, you can see this by squaring both sides. We have this equation, ST of the errors is equal to that. Now if we square both sides, that's the variance of the errors. And that says the variance of the errors is equal to 1 minus R squared times the variance of y. Okay? So that means that the sum of squares error is equal to 1 minus R squared times SST, which, right? In other words, 1 minus R squared is the fraction of the variance of y that's in the errors, which means R squared must be the fraction of the variance of the y that's predicted by the regression line, because they have to add up to 1. I mean, R squared plus 1 minus R squared is equal to 1. That's a tautology, right? And so if you want to multiply through by, so if you multiply through by, so if you say SST and multiply both of these by SST, you can say R squared times SST plus 1 minus R squared times SST is equal to SST. It's because of this relationship we had here. So the way you can remember it, I explained it better in the video, but the way you can remember it is, okay, R squared times SST and 1 minus R squared is equal to SST. So this is, this is a really easy way to fill out this chart if you're given R squared, which you usually are. So let's just do this example with all this information using R squared, okay? So we're given this, and this is our drink and GPA. And so there's R, so what's R squared? R squared is going to be 0.04. Okay. Now we're given that the standard deviation of y is equal to 0.5, and remember, and so if you square that, you get 0.25, and if you remember, SST is equal to n times the standard deviation y squared. So here's SDY squared, so we'll just multiply that by n, which is 25. So we have 25 times 0.25, and then this gives us 6.25. All right, so instead of doing what we just did here for 3 points, oh my goodness, it would take us forever if we did it for 25 each. So we have this information, and now we can fill out this chart, okay? So we've got SST right here. Remember, that's just n times SDY squared. And here's this is y, and this is x, so that was that squared, times n. All right, so we got 625. And now we have the r squared, so we'll just take 0.04 times that, times 6.25, and I got 0.25. All right, now what's 1 minus r squared? If r squared is 0.04, 1 minus r squared is 0.96, right? So now we'll multiply that. See, that's why together they're going to add up to this. So that gives 6. Okay, so this plus this adds up to that because 0.04 times these two add up to 1, r squared and 1 minus r squared. All right, now the degrees of freedom, p minus 1, I'm just going to have you, okay, n minus 1 for all of it. You know, because this is just deviation from the mean. 1 parameter, n minus 1, right? Now, here we have p minus 1 and n minus p, and you can see how they add up to n minus 1. P is 2 here. We have 2 parameters. So we have 2 minus 1 is 1. And n is 25 minus 2 is 23. Okay, so now we can get the mean square, 0.25 divided by 1. And here we have 6 divided by 23. And this is 0.261. So our F is what? 0.25 divided by 0.261, which is 0.958. All right. A much easier way of doing this we could have done is this. You can see why. It's the same thing as r squared. We could have done, I'll just show you right here, we could have done this. It would have been faster. We could have taken what? R squared, which was what? 0.04 divided by 0.96, and then just multiplied by 23 over 1, and you'll get the same thing, because that's basically what we did here. We should get the same thing. We should. 0.958. Anyway, that's to come, but that's exactly the same thing. You can see why. Because we have r squared over, we have this, the SSTs cancel out, right? And so you have this divided by its degrees of freedom over this divided by its. All right, so now let's just move on and take a deep breath. It's really not that hard. These complications, so we're going to test the null here, okay? And we'll look at the distribution of the F ratio. So here's our F. So now we have 2 sets of degrees of freedom. Here they are. So we have to follow the F curve with with what is it? Look at the table in the back of the book or find the actual p-value. So if we want to find the actual p-value, we have to look at the curve. What? Look at F curve with what? With degrees of freedom 1 in the numerator of 1 and degrees of freedom 2 in the denominator of 23, and see what our p-value is. So let's do that. Okay? So let's look at it. Whoops. So we'll go back to here, to the p-value, and now we're going to choose F, distribution. And numerator is 1. Denominator is what? 6? Is that what we said? No, 23. 23. And our F value was 0. F is always positive because it's squared. So it's 0. What? 958. And what do we get? So we compute the p-value, and we get 33.79. Write that down, 33.79. But let's just keep it up here because it says, okay, so the p-value is 33.79. It says, how does that compare to what we got from the t-test? So let's check it out. It's going to be like the two-sided t. Let's make sure. We already did that, but we're right here. So what are we going to do? T distribution, 23 degrees of freedom, and we had a t value of, I have to look back on page, here, I'll come over here. Let's go to the dock camera so I can show you where I'm looking. So I'm going to look back on page 130. I think we did it on page 137. Yes. So look back. Okay, how does that compare to the p-value we got from the t-test? So let's check it out by going back to page 137. We did this, and we got 16.36 for the one-sided. But for the two-sided, if we double that, we should get 33.79. Let's see, we got negative 0.98. It'll be close to that. So let's try it. So let's go to our PC, and we'll put in, whoops, that's right. We want to put in negative 0.98, negative 0.98, yep, negative 0.98. And we want a two-tailed. And what do we get? 33.73. So it's very close. We got 33. It's just a little bit of rounding error. So we get the same thing. Okay? So how does this compare to what we got from the t-test? So let's just write that down. So we'll go back to our document camera, and we will write that down. How does it compare? So p-value is this. So p-value, so p-value for F with 1 degree of freedom in the numerator and 23 in the denominator is equal to the p-value for T with 23 degrees of freedom, right, for two-sided test. And what was this value for, what did we get? So F was equal to 0.958, and our T statistic was negative 0.98. If we square that, T squared, we should get F. And T squared is equal to F with 1 degree of freedom here. For any T is equal to that. I didn't mean to do that, but it's the end. So anyways, it's the end. I think that people will think that's very strange, but see if I can get that back. Anyway, it is the end of the video, so you can hear me still. Guys, that was the end of the video, and we'll continue this and explain more next time. And please watch the pre-lecture.